In the previous lecture, we have arrived at the energy expression for a particle in a one-dimensional box. Furthermore, we have calculated the energy eigen function also. In this presentation, we have to talk about nodes and antinodes. Here, node is the position of minimum or zero displacement of the wave function, whereas antinode is the position of maximum displacement of the wave function. In the particle in a box problem, if the particle is making its to and fro motion, the motion of the particle is described in terms of wave function psi. Then the normalized wave function psi of x, which is equal to 2 by L inside the root sin n pi by L into x. For the occurrence of a node, the equation should satisfy the condition sin n pi by L into x equal to 0. If sin n pi by L into x equal to 0, then psi of x equal to 0. For that, the value of n pi by L into x equal to m pi. Here the value of m equal to 0, 1, 2, 3, then n. These are the values of m. If you put m equal to 0, n pi by L into x is 0. Therefore, sin 0 equal to 0. If you put m is equal to 1, the value of n pi by L into x equal to pi. Sin pi is also 0. From this, the value of x equal to m pi divided by n pi into L. This is equal to m L by n. If you put m is equal to 0, 1, 2, 3 up to m, we can get different values of x. If you put m is equal to 0, we can get x equal to 0. If you put m is equal to 1, you can get L by m. Then if you put m is equal to 2, we can get 2L by n. If we put m is equal to 3, we can get 3L by n. The series is going on, then the spectrum may end with n L by n. See here, these are all the positions of the nodes for the nth state. Here n stands for the quantum state. N is equal to 1 is the ground state, n equal to 2 is the first excited state, n equal to 3 is the second excited state. So, these are all the positions of the nodes for the given nth state. This is 0, n by n get cancelled, L. 0 is the initial point, L is the end point. You know that the particle is present within the spiral. X equal to 0 is one end of the wall, x equal to L is another one end of the wall. At the two ends, compulsorily, the value of the wave function is 0. So, nodal points are x equal to 0 and x equal to L. These two nodal points are compulsorily present in all the cases. In addition to these two nodal points, we may expect more nodal points. The availability of such nodal points are expected only on the basis of the value of n. Suppose n is equal to 1, that is specifying our ground state. N is equal to 1 means we can get x equal to 0 and x equal to L. We can get two nodal points. This is for n is equal to 1. This is for ground state. N is equal to 1 is our ground state. If I put n is equal to 2, then the position of the nodal points are 0, then L by 2, comma 2L by 2 is our L. We can get 3 nodal points. 3 nodes are present. If I say n is equal to 3, then the position of the nodes are x equal to 0, then L by 3, 2L by 3, and 3L by 3, L. In total, 4 nodes are present. N equal to 1, 2 nodes are present. If I say n equal to 2, then 3 nodes are present. N equal to 2 is the first excited state. First excited state. First excited state. N equal to 3 is our second excited state. Second excited state. So that for the given state, there are n plus 1 nodes. From this you may conclude that for the given state of n, there are n plus 1 nodes. Node is a position of minimum displacement of the wave function. Now we have to go for the term antinodes. Antinode is a point of maximum displacement of the wave function. For that, once again, we have to start our journey from the wave function psi of x. Psi of x, which is equal to 2 by L inside the root sin n pi by L into x. Root 2 by L is called our normalization constant. To get an antinode, the value of sin n pi by L into x could be equal to unity. Antinode is a point of maximum displacement of the wave function, so that sin n pi by L into x equal to 1. Therefore, n pi by L into x could be equal to 2m plus 1 into pi by 2. Here, the values of m are 0, 1, 2, 3 and so on. If you put m equal to 0, 2 into 0, 0, 0 plus 1, 1, then we can get pi by 2. Sin pi by 2 is equal to 1 because n pi by L into x equal to pi by 2 for n is equal to 0. If you put m is equal to 1, we can get 3 pi by 2. Sin 3 pi by 2 is also 1. From this, the value of x, which is equal to 2m plus 1 pi by 2 into L divided by n pi. This is equal to 2m plus 1 into L divided by 2n. If you put m is equal to 0, 1, 2, 3, 4, you can get the values of x, which is equal to see this m equal to 0, therefore L divided by 2n. If you put m equal to 1, we can get 3L divided by 2n. Then m equal to 2, we can get 5L by 2n. Next one is 7L divided by 2n. Then the series is going up. It ended with 2n minus 1 into L by 2n. In this term 2n minus 1 into L divided by 2n, if you put n is equal to 1, we can get L by 2n, the first term. If you put n is equal to 2, 4 minus 1, that is 3, L divided by 2n. 3 into L divided by 2n, the second term we can get. In this way, we can collect all the terms. These are all the positions of the antinodes for the given nth state. Suppose the value of n is given to you. N is equal to 1. We can get x equal to L by 2. Only one antinode we can get. This is the position of antinode. Suppose x equal to n equal to 2. This is ground state. This is first excited state. First excited. For this first excited state, we can get two antinodes. One is positioned at L divided by 4 and the second one is present at 3L divided by 4. See that n equal to 2. So that L by 4, 3L by 4. We can have two antinodes. Suppose n is equal to 3. This is second excited state. Second excited state. We can get three antinodes. Say x equal to L divided by 6 is one antinode. Then 3L by 6 is second antinode. And the third antinode is positioned at 5L divided by 6. For the given state of n, we can get n number of antinodes. But as far as our nodes are concerned, for the given state of n, we can get n plus 1 antinodes, n plus 1 nodes. But in the case of antinodes, for the given value of n, we can have only n antinodes. Now we have to go for the position probability. See, the position probability is psi star psi. In the case of probability density, that is psi star psi, antinode is the position of maximum probability density, which means that the particle is likely to present only at this point. If I say a node, this is the position of minimum probability density. That means the particle is not present at this point. Minimum is almost zero probability. Antinode is a point of maximum probability density, which means that the probability of finding the particle is maximum only at that point. If a point is specified as antinode, the probability of finding the particle at that point is maximum. If a point is specified as a node, the probability of finding the particle is 0 at that point. If you express the displacement in terms of wave function, node is a position of minimum displacement or zero displacement, antinode is a position of maximum displacement of the wave function. But in terms of probability density, that means the probability of finding the particle is called probability density. Antinode is a point at which we are expecting maximum probability density. That means the particle is likely to present at that point. If a point is specified as antinode, the particle is compulsorily present at that point. If a point is specified as a node, the probability of expecting the particle at that point is almost 0. This is the meaning for antinode and node in terms of probability density. If we express the psi star psi, we may say that for the given value of n, the probability density is also n. Suppose we can have n is equal to 4. The state is n is equal to 4, then we may get 4 antinodes. 4 antinodes. Say n is equal to 3, we can get 3 antinodes. If I say n is equal to 2, we can have 2 antinodes. If you think about the presence of nodes, usually x equal to 0 and x equal to L are the place where in which we can expect the nodes. In addition to that, in between two antinodes, one node should be present. One thing should be clear. In all the cases, in terms of probability density, the nodes are present at x equal to 0 and x equal to L. In addition to that, in between two antinodes, one node should be present. Suppose the number of nodes are n. We can expect n minus number of antinodes are n. We can expect n minus 1 nodes. In addition to the nodes, two nodes, one is present at 0 and another one is present at L. See that at the two ends, x equal to 0 and x equal to L, we can expect two nodes. In the case of probability density also. In addition to that, these two nodes, we may expect nodes in between two antinodes. If two antinodes are present, in between two antinodes, one node should be present. In this way, in addition to these two nodes, we can have n minus 1 nodes for the given value of n. In order to understand this concept more, we should go to the pictorial representation. Anyway, in the case of classical view, the particle is present anywhere else within the potential, but in terms of quantum aspect, the particle is present only in the specific places because the energy is quantized. In the case of classical accelerator, energy is not quantized, whereas in the case of quantum accelerator, energy is quantized. Please go through this diagram. You may understand more about the relation between the wave function and the probability density. See this first diagram, which is specifying the wave function n equal to 1, n equal to 2, n equal to 3, n equal to 4. The corresponding wave functions are psi 1, psi 2, psi 3 and psi 4. For the value of n is equal to 1, we can have only one node, one antinode. That means the position of maximum displacement. If n equal to 2, we can get two antinodes. 1, 2. n equal to 3, we can have three antinodes. 1, 2, 3. For n equal to 4, we can have four antinodes. 1, 2, 3 and 4. Suppose the value of n is equal to 1, we can get two nodes. X equal to 0, one node, x equal to L, another one node. Suppose n is equal to 2, we can have three nodes, x equal to 0 and x equal to L. In addition to these two nodes, at the middle we can have one node. Suppose n equal to 3, in total we can have 4 nodes. n equal to 4, we can have 5 nodes. In all the cases, at x equal to 0 and x equal to L, compulsorily we have had 2 nodes. This is the wave function diagram. This is the probability density diagram. See this. This is for n equal to 1, absolute square of psi 1. This is n equal to 2, absolute square of psi 2. This is n equal to 3, absolute square of psi 3. n equal to 4, absolute square of psi 4. For the given value of n equal to 1, we are having only one antinode. For the given value of n equal to 2, we are having two antinodes. n equal to 3, we are having three antinodes. n equal to 4, we are having four antinodes. Here antinode is the point corresponding to the maximum probability density. That means the probability of finding the particle is more at these 4 points. The particle is likely to present on all these 4 points. If n equal to 3, the particle is likely to present in all these 3 points. If n is equal to 2, the particle is likely to present only at these 2 points. If n is equal to 1, the particle is likely to present only at this point. Say that as pointed out earlier, x equal to 0 and x equal to L are the positions of two nodes. In addition to that, nodes are present in between two antinodes. See this, n is equal to 2 state. At x equal to 0, one node is present. At x equal to L, another node is present. But the third node is present at this point, which is present in between these two antinodes. The same case is true for all others. So that in the case of classical view, the particle is likely to present anywhere within the well, but as far as the quantum view, the particle is confined to present only at few specified points. The probability of finding the particle is not uniform at all the points. It is confined to few points. That's all about the nodes and antinodes. Thank you.